Performance analysis of air conditioner using R290 as refrigerant with and without nanoparticles. Abstract R22 is commonly used refrigerant in air conditioning systems. These HCFC refrigerants have negative impact on the environment which causes ozone depletion. Hence the usage of these HCFC refrigerants needs to be avoided. An alternative refrigerant need to be evaluated as an alternative to these HCFC refrigerants, and R290 is suitable as alternative refrigerant due to its low ODP and low GWP. In this, Cu-doped MgO nanoparticles are synthesized and the nanoparticles are used for the preparation of nano-lubricant with different concentrations. An experimental investigation is performed on the air conditioner using R290 as refrigerant with and without Cu-doped MgO nanoparticles in compressor lubricant oil. The system performance is analyzed and compared with and without using nanoparticles based on the performance parameters such as refrigeration effect, compressor work input and COP. Keywords R22, R290, GWP, ODP, nanoparticles, refrigeration effect, compressor work input, COP. Introduction. To improve the coefficient of performance, COP, of the vapor compression refrigeration system, VCRs, different methods are adopted as reported in the literature. Bilirnajahan and Kurzad Ersoy, 2009, have studied the role of a two-phase constant area of the ejector for improvement in the performance of a refrigeration system by recovering the kinetic energy at expansion process, and as a result reducing the compressor work. Satter et al., 2007, has reported the performance improvement of a VCRs utilizing refrigerant R134A when various blends of hydrocarbons are used. With the advent of nanotechnology, in the literature survey, many have studied the effect of nanoparticles as additives in refrigerant or in mineral oil used as the lubricant, on the COP of the VCRs. Park and Jung, 2007, studied due to the addition of the carbon nanotubes the boiling heat transfer in refrigerants enhanced. Lee et al., 2009, has stated an improvement in the lubrication characteristics is found when the refrigeration mineral oil containing 0.1 vol% of full-René nanoparticles. By et al., 2008, studied that when 0.1% mass fraction of TiO2 nanoparticles in R134A and polyester, PO, oil system are used in the VCRs has reduced the power consumption about 26%. Stability of nanoparticles in suspension is one of the key issues which make the application of nanoparticles and undergoes a phase change in every cycle. Lubricants enhance the performance of a system in several ways when additives are added to it. When the nanoparticles are added to lubricants, the critical parameters improved are anti-friction, anti-wear, anti-corrosion, extreme pressure, detergent and antioxidant. With increasing complications in operating conditions and development in technology coupled with increasing lubrication requirements are the necessary factors for the exploration of the new kind of additives and optimum value of their concentrations. Nanoparticles are regarded as the most important prospect to meet these demands. The performance of composites, oils, fluids, etc. are enhanced due to the addition of nanoparticles, which is due to high surface area to volume ratio that is leading to the extensive interaction between tribo contact points and lubricants containing nanoparticles. 2. Preparation of nano-lubricant. MgO is an important material that has wide range of applications in catalysis, toxic waste, remediation, paints, superconducting products, and antibacterial activities. The MgO compound has boiling point about 3600 degrees C and melting point as 2852 degrees C. These oxide materials can be synthesized by different methods like solution combustion, chemical precipitation, sol gel, hydrothermal, soluthermal, microwave-assisted sol gel, and green synthesis etc. Among these methods, CO precipitation method is one of the best methods to synthesis nanoparticles without agglomeration in the production. Cu-doped MgO nanoparticles will be prepared by CO precipitation method. The samples were synthesized under laboratory conditions in clean room and analyzed using such as X-ray diffraction, XRD, and scanning electron microscopy, SEM. A synthesis and analysis of Cu-doped MgO nanoparticles. Prepare a solution mixture of 0.6 m magnesium chloride and 0.01 m copper chloride. Also prepare 0.1 m KOH solution. Mix KOH solution drop-wise to the mixture solution of magnesium chloride and copper chloride and kept under constant stirring for 3 hours, then we obtain a green bluish thick solution. Refrigerants difficult, but it is also hard because the fluid. Then the solution is filtered and we obtain green bluish precipitate. The precipitate is dried in oven at 100 degrees Celsius for 3 hours and then calcined at 200 degrees Celsius for 2 hours. Thus Cu-doped MgO nanoparticles are obtained. SEM analysis of the Cu-doped MgO shows that the nanoparticles are agglomerated due to the defects created by Cu doping. With the increase in the dopant concentration, the agglomeration of particles takes place. Thereby the size of the nanoparticles will be increased when compared with pure MgO nanoparticles. B. Preparation of Cu-doped MgO Nano-lubricant. Cu-doped MgO nanoparticles are added to the compressor lubricant oil in the refrigeration system. The preparation and stability of this lubricant and nanoparticle mixture is more important to the given study. The lubricant oil, commonly used in the refrigeration systems, was PO oil. This oil is selected owing to its common usage and superior quality. Ultrasonic vibration method is used to stabilize the dispersion of the nanoparticles in the lubricant. The steps are involved in the preparation of nano-lubricant is as follows. Cu-doped MgO nanoparticles are weighed using digital electronic balance with the measurement ranging from 12 mg to 200 mg. Add Cu-doped MgO nanoparticles into the PO oil and get the Cu-doped MgO/PO oil. By using an ultrasonic vibrating system, the mixture is vibrated for few hours and as a result Cu-doped MgO nanoparticles will get dispersed well into the lubricant oil. The surfactant is not added to this mixture because it may decrease the thermal conductivity and the performance of the system. The oil container is kept in the magnetic stirrer to get the homogenization of nano-lubricant. Nanoparticles, Cu-doped MgO, with 0.2, 0.3 and 0.4 vol. % is added to the PO oil and tested in the setup are prescribed. 3. Experimental work. The study was conducted on air conditioning test rig. The test rig consists of a compressor, air-cooled condenser, capillary tube, and an evaporator. The compressor was hermetically sealed reciprocating compressor and the evaporator made of copper. The heat flux was supplied to evaporator by means of heater, 230 W, an automatic stirrer to continuously stir the water. The condenser was cooled using fan. The pressure gauges were installed at the salient point of the refrigeration system. Thermocouples were used to measure temperature at various locations of the flow of refrigerant. The power consumption by the compressor was measured using energy meter. The heater power regulator is provided to adjust constant heat flux and maintain steady state condition. The test rig was filled with N2 gas at a pressure of 200 psi and this pressure was maintained for 5 HRS. The system was checked for the leakages thoroughly using traditional soap bubble method and ensured for no leakages. The system was evacuated by removing N2 gas. A vacuum pump was connected to the port provided in the compressor and the system was completely evacuated for the removal of any impurities. This process was carried out for all the trials. The compressor was filled with the PO oil and the refrigerant R290 was charged through the charging line to the compressor. Every time the system was allowed to stabilize for 15 minutes. The tests are conducted on the air conditioner test rig in the following cases by maintain the evaporator exit temperature T1 constant at 20 degrees Celsius, 25 degrees Celsius, and 30 degrees Celsius. Case I, air conditioning system using R290 as refrigerant and PO oil as compressor lubricant. Case 2, air conditioning system using R290 as refrigerant and PO oil with Cu-doped MgO nanoparticle, 0.2% volume, as lubricant. Case 3, air conditioning system using R290 as refrigerant and PO oil with Cu-doped MgO nanoparticle, 0.4% volume, as lubricant. Case 4, air conditioning system using R290 as refrigerant and PO oil with Cu-doped MgO nanoparticle, 0.6% volume, as lubricant. 4 results and discussion. A comparison of net refrigeration effect. When the air conditioning system is operated at constant evaporator exit temperature, T1, of about 20 degrees C, with the increase in concentration of the nanoparticles in the lubricant oil, the net refrigeration effect of the system increased from 345.154 kJ/kg to 350.3 kJ/kg. Similarly, when the T1 is maintained at 25 degrees C and 30 degrees C, the net refrigeration effect of the system increased from 349.532 kJ/kg to 361.999 kJ/kg and from 352.437 kJ/kg to 371.05 kJ/kg respectively. Hence the percentage increase in the net refrigeration effect of the system when T1 is maintained at 20 degrees C, 25 degrees C, and 30 degrees C is 1.49%, 3.57% and 5.28% respectively. B. Comparison of compressor work input. When the air conditioning system is operated at constant evaporator exit temperature, T1, of about 20 degrees C, with the increase in concentration of the nanoparticles in the lubricant oil, the power input to the system decreased from 81.711 kJ/kg to 77.956 kJ/kg. Similarly, when the T1 is maintained at 25°C and 30°C, the power input to the system decreased from 80.452 kJ/kg to 79.057 kJ/kg and from 80.374 kJ/kg to 78.591 kJ/kg respectively. Hence the percentage decrease in the power input to the system when T1 is maintained at 20°C, 25°C and 30°C is 4.6%, 1.73% and 2.22% respectively. See comparison of compression pressure ratio. The compression ratio of the system increases with the increase in the volume concentration of the Cu-doped MgO nanoparticles in the PO lubricant oil. As the evaporator temperature increases from 20°C to 30°C and the nanoparticles concentration increases from 0% to 0.6% in lubricant oil, the compression ratio increased from 3.671 to 5.417. D. Comparison of coefficient of performance, COP. When the air conditioning system is operated at constant evaporator exit temperature, T1, of about 20°C, with the increase in concentration of the nanoparticles in the lubricant oil, the COP of the system increased from 4.22 to 4.499. Similarly, when the T1 is maintained at 25°C and 30°C, the COP of the system increased from 4.345 to 4.759 and from 4.545 to 4.721 respectively. Hence the percentage increase in the power input to the system when T1 is maintained at 20°C, 25°C and 30°C is 6.611%, 5.385% and 7.669% respectively. V. Conclusion. The study results statement and its contributions are concluded in following points. A hybrid nanoparticle Cu-doped MgO is synthesized and it is used to prepare the nano-lubricant that reduces the compressor work. Nano-lubricant is prepared by mixing the Cu-doped MgO nanoparticles at 0.2% vol, 0.4% vol, and 0.6% vol concentrations with the polyester oil. The performance of the refrigeration system is evaluated by maintaining the evaporator temperature at 20°C, 25°C, and 30°C. COP is increased when R290 along with nano-lubricant is used in the VCRs as compared to that of only R290 refrigerant. It is observed that the compressor work input decreased from 81.711 kJ/kg to 78.591 kJ/kg as the concentration of the lubricant oil increased from 0% vol to 0.6% vol. The increase in COP of system when 0.2% vol and 0.6% vol of nanoparticles is used more when compared to the increase in COP of system when 0.4% vol of nanoparticles. The maximum increase in the COP of the system is 7.669% and it is observed when 0.6% vol of the Cu-doped MgO nanoparticles with PO oil at 30°C of evaporator temperature. The least increase in COP of system is 1.128 and it is observed when 0.4% vol of the Cu-doped MgO nanoparticles at 25°C of evaporator temperature.